Okay, now it's okay.
Okay, so welcome everyone to today's seminar. Today we have Mathias Schreiber, who is at Universidad Técnica Federico Santa María in Valparaíso in Chile. We have also a very similar university name in our state. So some people might think it's in Brazil, but no, this is in Chile. Mathias, he got his PhD at the University of Göttingen in Germany. And then he held postdoc positions in Cape Town in South Africa, in Strasbourg in France, and Potsdam in Germany, before going on to Chile at the Universidad de Valparaíso, in the same city as the university he is today. So thank you so much, Mathias, for accepting our invitation. The floor is yours when you're ready.
Thank you very much. I would like to start with a question. What do we see on my first slide? What do we see on this slide? Everybody, academics, students, we have seen this image, but what do we see? It's not a rhetorical question. I want you to answer.
The sun? It's an eclipse, solar eclipse. It's the sun.
It's a solar eclipse, very well. And what is this bright stuff we see around the moon? So the sun is eclipsed, but what do we see?
Magnetic field.
The corona, exactly. We see the corona, and the particles in the corona, which are mostly electrons and protons, are connected to the magnetic field lines of the sun. And so we see, due to Thomson scattering, these particles scatter the sunlight towards us. We see the structure of the magnetic field. And actually, we even see that far beyond the solar radius, the particles are connected to the field lines. And that means that at this large distance, they rotate with the same angular velocity as the sun is rotating. So when they finally leave the corona and become the solar wind, we all know, these particles take away more specific angular momentum than they had on the surface of the sun. This means the sun is losing angular momentum. And this process is one of the most fundamental processes in stellar astrophysics, according to me at least, and it's called magnetic braking. And this magnetic braking is reducing over time the rotation rate of stars, of all stars that have masses below 1.4 solar masses, and they are active, they have a corona, they have a magnetic field, and these stars slowly rotate slower. The rotation period is increasing. And why is this important? Because it is important, if we understand this process, actually it may allow us to measure, for example, stellar ages due to a process which is called gyrochronology. These active stars, why can I not? These active stars have star spots, like the sun has spots, and these are dark regions which are less bright. So if these spots rotate into view and rotate out of view, we see a variability of the star. And this variability is relatively easy to measure. You see on the right, relatively old measurements of rotation periods of stars. And if we know with which rotation period a star is born and how it's becoming slower over time, we can measure the age. And measuring the age is a very important topic in stellar astrophysics because it's hard otherwise. So gyrochronology is actually a powerful tool to measure rotation rates, and that's one of the reasons why magnetic braking is so important. Why is it important to know stellar ages? For example, to reconstruct the star formation history of the solar system, of the Milky Way, sorry. So, and this has been done with gyrochronology. By measuring the ages of different groups of stars, you can reconstruct the star formation history, and it has been found that especially when the Sagittarius dwarf galaxy is crossing through the Milky Way, we have bursts of star formation in the Milky Way, like 6 billion years ago, 2 and 1 billion years ago. So it's clearly a powerful tool, understanding how stars rotate slower over time. It's not only important for understanding the evolution of our Milky Way, it's also important in a very different context. For example, if you search for planets that might host life. In this context, it's also important to know the age, because if we look, for example, at the Earth, biosignatures in the Earth have become visible only a few billion years ago. 2.4 billion years ago, the atmosphere became oxygen-rich. Before, it was hard to see that there has been a lot of photosphere, oxygen produced by plants on Earth. This is only 2.4 gigayears old. So if you look in exoplanets for biosignatures, you better know that the star is 2 gigayears old or a bit older, so that the planets around them had the opportunity to develop life as we know it. In a similar context, if we understand the evolution of rotation of stars, we can estimate, or we can understand for how long they emit X-ray and extreme ultraviolet radiation. And this can be harmful to life. So the habitability of planets around these active stars depends on their rotation rate. So it's good to know how fast they rotate, for how long, and how do they slow down over time. And now, last but not least, magnetic braking is of fundamental importance for binary stars. In binary stars, it drives the evolution and the production of supernovae, important for cosmology because it led to the discovery of dark energy, or the main sources of gravitational waves that we expect to detect with laser space interferometers like LISA. These will be closed binaries, and the formation and evolution of these closed binaries depends largely on magnetic braking. I will explain in a bit more detail why that is. So if you now accept that magnetic braking is important, because not everybody is familiar with magnetic braking, but it is important from the habitability of planets to the formation of our galaxy to binary star evolution, then you might think, let's just calculate it. And we can try this. Yeah. So let's just calculate magnetic braking. We have the angular momentum loss here in the top line, should be somehow proportional to the magnetic wind mass loss, the velocity, the tangential velocity at the Alfvén radius, and the Alfvén radius. You can replace the velocity with the rotation period and another Alfvén radius, and you get this equation. And this looks really simple, so it should be simple to estimate. However, the big problem is we do not even properly understand how magnetic fields are generated in stars. So we do not know, if we start from the bottom equation here, we do not know how the magnetic field strength depends on mass, radius, or rotation rate of a star. We have not even clear what is the main dynamo mechanism. Is it an alpha omega dynamo? Is it an alpha square dynamo? There are many different dynamo types that have been proposed, and we are not sure which one is the dominating one. So we don't know the field strengths, and we don't know how the wind actually depends on field strength, mass, radius, rotation rate, and even the Alfvén radius, we are not sure how it depends on these basic properties. So if all of these quantities in the main equation we do not properly know, we cannot calculate magnetic braking. So this is sad on one hand because it's so important, but on the other hand we can also say maybe if we are able to derive empirical relations for magnetic braking, we might use these empirical relations to inform people working on dynamo theory. So from studying magnetic braking with a more empirical approach, we might learn something about dynamo physics. So for example, if a fully convective star or a star that's only partially convective, if they have the same dynamo is not clear. But if they have the same type of magnetic braking, probably they have a similar dynamo. If, on the other hand, magnetic braking is very different for fully convective stars and for partially convective stars, then maybe the dynamos are different. So it can be useful to use empirical relations to inform dynamo theories. Unfortunately, until relatively recently, the situation of the empirical magnetic braking prescriptions was kind of sad because it looked more or less like this. So here you have, in this case for a binary star, you have on the y-axis the angular momentum loss, and here the donor mass, which is the star that is suffering from magnetic braking. And you see all these different lines, we don't go into the details, all these different lines represent suggested empirical relations for magnetic braking. And you see they differ by more than 7 orders of magnitude. So basically, everybody who has a problem with a single star or a binary star and wants to understand the evolution, or a sample of one type of binary stars or single stars, and wants to understand the evolution, is creating its own prescription for magnetic braking, which then, of course, doesn't help really to understand it and to inform dynamo theories. So with this, we are basically lost. However, in the last few years, there have been more and more attempts to unify magnetic braking prescriptions. These attempts have been separated, have been proceeded separately, one for single stars in the single star community and one in the binary star community. So I will discuss now the two constraints, the two different types of constraints that are available for from single stars and from binaries separately. So let's start with single stars. Magnetic braking in single stars, what can we learn from single stars about magnetic braking? So the first empirical relation that has been found for magnetic braking goes back to 1972, famous paper by Skumanich. Basically, 2 clusters and the sun, you have 3 points. You can fit power law and you get that the rotation period is decreasing over time with the square root of h, of the age of the star. And then with a little bit of algebra, you can convert this relation to an angular momentum loss rate, which then depends on the mass, radius, and to the -3 of the rotation period. So the slower the star rotates, the less efficient magnetic braking is. The longer the rotation period is, the slower, the weaker magnetic braking. So this has been the first relation, has been used for decades. But of course, it's just for one type of star, for solar type stars, and it's just for slowly rotating stars. Later, I think starting 2000, 2005, 2010, it has become more and more clear that activity indicators actually do not follow this dependence on rotation period for a long time. Actually, they saturate, we say. So what is saturation? Here we see different activity indicators, the magnetic flux on the left, the X-ray luminosity, and the flare rate. So how many flares are counted over time, or a certain period of time. And all this as a function of Rossby number. And the Rossby number is the rotation period divided by the convective turnover time. So on the left in each diagram, you see rapidly rotating stars, and on the right, you see slowly rotating stars. So as long as they are slowly rotating, it's actually similar to what Skumanich predicted, that magnetic braking or the magnetic flux or X-ray luminosity or the flare rate are actually increasing with faster rotation. But at a certain moment, this process seems to saturate. This is true for the magnetic flux, this is true for the X-ray luminosity, and it's true for the flare rate. So all activity indicators seem to saturate, and then the natural idea is, magnetic braking should probably saturate as well, because that's basically this stuff that is related to magnetic braking. So it's reasonable to assume, oh, maybe magnetic braking saturates as well. And saturated magnetic braking prescriptions are actually now leading in single star evolution, actually also in binaries, as we will see later. So magnetic braking saturates, and then actually it works quite well. This is a famous paper from Chalmette in 2015, where he made a model according to this saturated magnetic braking prescription. And you see here the rotation period as a function of mass. And he evolved a number of stars. And so with time, they become slower. And then he got this distribution at the end. And you see here the black diamonds are the predicted rotation rates, and the red stars are the measured rotation rate at a similar age of one cluster. And the dotted line represents the saturation period, which is not the same for all masses. It depends on the mass. So these stars here on the left, they evolve relatively quickly in the saturated regime towards this region here between the green and the blue line, and then they accumulate here because magnetic braking becomes weaker the slower the star gets. And that
O
actually
mapa te mandou para uma viagem mais longa.
Qual é que tu me sugere?
Não, agora já passamos ali, era só subir reto.
Excuse me? Is there a question?
Was asking a question?
No.
Okay. Sorry, it
No.
was some disturbance. You can continue.
Yeah. I just continue. So you see that this is a relatively good representation, except of these outliers here. And later, as in the last 10 years, it has been shown that this actually works. You can use cluster data. So you know the age of a number of stars because they are in a cluster. And then you measure the rotation rate, and you see that if you go to older and older clusters, the stars become slower and slower, and you can actually derive an empirical relation how stars break as a function of their mass or their color or their temperature. And then the next big step, of course, is can we prove this somehow? And there was a very nice paper recently from Gruner et al., who actually used white binary stars. So two stars that are in white binaries, they must have been born together, and then they should have the same age, right? So you can use one of these stars and measure the rotation rate, and then see in this cluster calibration that you made, right? This is different age groups that you defined. The different colors are different age groups that have been defined through measurements of rotation rates in clusters. And then you can see if the companion star has the same age. And then actually you think, wow, it works because they have the similar age derived independently from rotation. And the lines here connect always to companions. And you see that hardly always and never there is a green line connected with a blue one or orange with blue. It's always blue with blue, green with green, orange with orange. And so this means in general it works. We can use the rotation rate to measure ages. And actually they really also with the same calibration, they measured the star formation history in our galaxy. So it seems they are doing well in single stars, and they are converging towards a saturated magnetic braking prescription. There are, however, a few complications. One, for example, is that if you look at the clusters, here's now like a study of where you see the different clusters. Here you have the rotation period. This is from Curtis et al. Rotation period, this time as a function of effective temperature. And the different colors are different ages again from different clusters that are here listed in the inlet. So you see that in general, the older the cluster, the longer the rotation period. So the stars slow down. Makes entirely sense. But for some clusters, they overlap in this range here between 5,500 and 4,000, 3,000 Kelvin. The green, the orange, and the yellow stars, which covers more than a gigayear, roughly a gigayear, is actually the same. So there seems to be some time where this magnetic braking doesn't work anymore. And then it continues again. This is, of course, a big mystery. It has been incorporated, it is thought now, and it works relatively well, that this has to do with angular momentum exchange between the radiative core and the convective envelope. So the idea is the core is rotating fast initially, and then the envelope is actually suffering from magnetic braking. So it's not like a rigid body, which always rotates like a ball. It is actually that there is some inner structure and inner angular momentum transport in the star. So if the core rotates faster, it always injects a little bit angular momentum into the slower envelope due to friction. And at some point, this injection of angular momentum in the envelope can actually compensate the magnetic braking that the envelope is experiencing. And this is the idea that this is explaining this so-called stalling of magnetic braking at these ages. So it's an interaction between the radiative core and the convective envelope that not necessarily rotate with the same velocity. And in single stars, the core is assumed to rotate faster. because only the envelope is feeling the magnetic braking. And last but not least, I talked about different dynamos for fully convective and partially convective stars. Does magnetic braking in single stars change at the fully convective boundary? And it seems so, yes. Very nice Nature paper from last year in Lu et al. They separated partially convective and fully convective stars. And here now we see the rotation period as a function of age. And the red points are the fully convective stars, so masses lower than 0.35 solar masses, so really late M dwarfs. And partially convective stars are in red, in black, which have masses above 0.35 typically. And if you use low temperatures, you have mostly fully convective stars, and they have, even at relatively low ages, already quite long rotation periods. Then you go to slightly higher temperatures, you have a mixture of both, and you see that the black ones, the partially convective ones, are systematically below the red ones. So they have less efficient braking in partially convective stars. And if you go to even higher temperatures, you hardly have any fully convective stars. You're dominated by the partially convective ones, and they rotate faster. So the idea is that at the fully convective boundary, magnetic braking becomes more efficient. Fully convective stars brake more efficiently than partially convective stars. This argues actually that there is potentially a different dynamo in action. However, there are actually two schools. One says, no, this shows that these dynamos are different, but then others say the stuff I showed about the saturation actually works for fully convective and for partially convective stars. So for both types of stars, we have the same relation and the same limit for saturation, and this argues for the same dynamo. So it's not yet clear. But at least in terms of the efficiency of magnetic braking, it seems something is happening at the fully convective boundary. Okay, so from single stars we learned a difference. Fully convective stars are braking more efficiently. We have gyrochronology, which in general works. We can determine the ages. And we have some interaction between the core and the envelope to explain this stalling. And so this is basically, and magnetic braking is saturated, which means the dependence on periods is relatively shallow for fast rotating systems. So this is one school, and they seem to converge towards a proper understanding of at least empirical relations for magnetic braking. So now the drama starts if we look at binaries, because as you will notice, things are very different. The first thing in closed binaries that is very different is that you have tidal forces. And these tidal forces actually cause synchronous rotation. So if you have a star, which consists, for example, of a white dwarf and a normal main sequence star that is active, so it has magnetic braking, this star says, and the orbital period must be below 10 days. So this star then says, yeah, I want to rotate slow because I'm losing angular momentum through this wind. But the white dwarf actually says, no, you can't, because there are tidal forces that force you to rotate with the same period as the orbital period. And this means that the angular momentum has to be taken from something else. It cannot be taken from the rotation because the rotation is fixed due to the tidal forces. And so the angular momentum is taken from the orbit. So instead of rotating slower, actually the star is rotating faster because the orbital period is decreasing and decreasing due to the action of magnetic braking. Because the angular momentum is taken from the orbital motion and not from the rotation of one of the stars. If you do the same now with the famous Skumanich law I mentioned earlier, you have this blue line which represents like the Skumanich braking law, the first empirical prescription ever invented. You get this angular momentum loss. And if you use the same angular momentum loss now, but for the orbit, you get for the spin period, for the rotation period of the donor star in the example we have just seen, you get that with time, it's rotating faster and faster and faster, and this is because the orbit shrinks. So we have a big difference. In single stars, braking makes the star rotate slower, as you expect. In binaries, it's the other way around. The companion stars that still are active, so low mass stars, rotate faster because the angular momentum is taken from the orbit. And this is a fundamental process for binary evolution because it drives the orbital evolution of nearly all binaries that contain a neutron star, a black hole, a white dwarf. All of these objects, virtually all of these objects, at some point, the orbital evolution of these objects is driven by magnetic braking. So on the next slide, I will illustrate this. Don't get scared. It's a very dense figure. You don't need to understand the entire figure. I just want to illustrate at which stages magnetic braking becomes important. So this is now from a paper from my postdoc Diogo Belloni and myself, a review paper on binary evolution. And this is basically all that can happen to two stars that start as main sequence stars, and if they evolve further. And this contains high mass X-ray binaries, low mass X-ray binaries, double white dwarfs, cataclysmic variables, all these type of stars, and the evolutionary pathways are illustrated on this slide. It's not important to understand the details. Just want to highlight at which stages magnetic braking is important, and it's basically always as long as there is a low mass star. So we really need to understand magnetic braking to progress with our understanding of closed binary evolution. And well, we cannot measure the rotation rates. We could, but the rotation rates are fixed by the orbit. But what we can do is we can learn about magnetic braking by looking at period distributions. Because, as I just explained, the stars evolve due to the loss of angular momentum from magnetic braking. They evolve from longer to shorter periods. And this actually means that if we have one type of system where we can measure many orbital periods, the distribution of orbital periods will tell us something about the strength of magnetic braking. And the best systems to do that are actually called cataclysmic variables. Cataclysmic variables are the most abundant systems in which a white dwarf and a main sequence star are present. We think they look something like that. So there's a white dwarf that is accreting from a companion star, and there's Roche lobe overflow from this companion star, and then if there is no strong magnetic field of the white dwarf, the material is accreted onto the white dwarf through an accretion disk. And in these systems, the evolution from longer to shorter periods is driven by angular momentum loss, and the mass transfer, so how much mass is transferred, is also driven by angular momentum loss due to magnetic braking. So it has been for decades an exercise to look at the orbital period distribution of these objects and to see what can we learn about magnetic braking. And here you see the orbital period distribution measured in 2011 didn't change much since then. So the left plot shows the period distribution, and you see there are many systems with periods shorter than 2 hours. Some systems, so the black line is all systems, the red is a subtype of cataclysmic variables. It doesn't matter in the context of this talk. So you just take the black line and you see some systems here with periods longer than 3 hours, and then you see many systems with periods below 2 hours, but there is nothing in between. And so this has to be something to do with magnetic braking or with the way these systems lose angular momentum, because angular momentum drives the evolution from longer periods here on the right to shorter periods. But why do we see very few here in the middle? The idea has been actually since the 80s. It's a very old idea. The idea is that here for stars, when the companion star that is losing mass still has a radiative core, magnetic braking is very strong, as predicted by Skumanich. So this is all the saturated regime. So it was usually assumed, no, we have no saturation. Let's extend Skumanich, and because these are short periods, you get very high rates of angular momentum loss. So here you have very high rates of angular momentum loss, and then the mass of the donor star is decreasing while they evolve from longer to shorter periods, and as the mass is decreasing, it becomes closer and closer to the fully convective boundary. And if it reaches the fully convective boundary, something happens to the dynamo and magnetic braking decreases significantly or turns off completely. And if that happens, actually, you can reproduce this gap. And the idea is that due to the high mass transfer, the donor star is out of thermal equilibrium. So it's larger than it actually should be for its mass when they are at long periods here with strong magnetic braking. and then suddenly they become fully convective, and magnetic braking turns off. So the mass transfer timescale becomes longer than the thermal timescale, and the star has time to relax to its equilibrium radius. That means it detaches from its Roche lobe, and then it evolves as a detached system through the orbital period gap. And then when they become closer and closer, and when they are close enough to start mass transfer again, you see them again as a CV when they have periods below 2 hours. This is standard theory for cataclysmic variable evolution. And yeah, it has been criticized a lot, but it survived since the 80s. So it is there is some truth in it, and there's actually independent evidence. You might say this cannot be true because we just learned in single stars, magnetic braking becomes stronger when we go to fully convective stars. Here in binary stars, the opposite is assumed. Magnetic braking is dramatically decreased at the fully convective boundary to explain this period gap. So you can say, no, that doesn't make sense. But there is independent evidence that this is actually happening. So we looked at stars where there is no mass transfer yet. So both stars are still separated, no accretion going on. And in this sample, you should see the ones that here in between 3 and 2 hours are passing actually through the period gap, the detached CVs, you could say, where there's no accretion. You should see them in this sample. And actually, that's exactly what we did. Here on the left, you see measurements of detached systems, a white dwarf plus an M dwarf. And you see between 2 and 3 hours, you have this high white dwarf masses and an excess of systems in this period range. And you can only explain this excess if you include, like in the models in the middle and on the right, if you include these CVs that evolve detached through this phase, because these high masses are actually typical CV masses. So in the gray scale in the background is the model, and the red dots are the measurements. You can only explain these measurements here if indeed CVs evolve as detached systems through the gap. So at least the idea that something is happening at the gap when the star becomes fully convective is true, and it works if you assume magnetic braking becomes less efficient. Here is another evidence that magnetic braking is stronger for partially convective stars. This is like the fraction of these detached systems as a function of all systems. All systems means all white dwarf main sequence binaries can be very separated or very close. And this is a fraction of the close ones. And the fraction of the close ones is high if the companion star is fully convective, between 0.1 and 0.35 masses. So if it is fully convective, you see many of these closed systems. If it's partially convective, you see a few. And the idea is we see a few because magnetic braking is strong, they evolve fast. And then for fully convective stars, we see many because they evolve slow. Because magnetic braking is inefficient, they evolve slowly towards shorter periods. So this makes entirely sense. And it gets even better because there has been a prediction. If this idea of magnetic braking gets disrupted at the fully convective boundary is true, we should see a difference in the period distribution of CVs where we have a strongly magnetic white dwarf and systems where we don't have a strongly magnetic white dwarf. So, and this is true. Here you see now in the background, the gray histogram is the period distribution of CVs when the white dwarf is not magnetic. So you see, and the black line is a cumulative distribution. You see it rises here and then it becomes flat in the gap. So we don't see many systems in the gap as in the previous period distribution I've shown. And then you have systems when you are at longer periods than 3 hours. If you now look at the red line, this is the same type of systems, but the white dwarf has a strong magnetic field, like hundreds of megagauss. So really strongly magnetic. And if you look at these systems, you don't see the period gap. It's just a continuous distribution. And actually, this has been predicted by disruptive magnetic braking in the 90s. We have measured it only recently, but it has been predicted a long time ago by Lee et al. And if the white dwarf here on the left has a strong magnetic field and can capture field lines of the donor star and then reduces the wind regions. So you need a wind to have magnetic braking. But if the magnetic field of the white dwarf is capturing all the wind, you don't have efficient magnetic braking. The wind zone in this example here becomes very small. Just this region you can have efficient angular momentum loss. And if the magnetic field is even stronger, you can suppress magnetic braking completely due to the strong magnetic field of the white dwarf. And if you don't have strong magnetic braking, you don't have the increased radius, and then you cannot have the reduction in radius when magnetic braking turns off, so you don't have a period gap. Actually, it tells us it must be a magnetic effect that is explaining the period gap. So we have, from the perspective of binary people, we have perfect evidence that at the fully convective boundary, magnetic braking is dramatically reduced. Single star people have perfect evidence that if you go to fully convective stars, magnetic braking is increasing. There is obviously something fundamental we do not understand. And I already tell you, I don't have the solution. Okay, so this was all working relatively well using the old prescription from Skumanich, 72. So, and then recently, El Badri in 21 showed that this relation is not true for binaries, because also in binaries we have saturation. So here you see the period distribution, the number of systems per period bin as a function of orbital period, which is equal to the rotation period for these binaries. And this is only main sequence binaries, so 2 main sequence stars. And you see all distributions are flat. And this means you cannot have a strong dependence of the braking on period, exactly as predicted by saturation. If you had this Skumanich law, you would see something like the dashed line here, the dashed purple line. You would expect a strong dependence on period, because the shorter the period, the faster the stars would evolve. So this is actually evidence that saturation is true, and also for binaries. So all the models we did for close binaries that used the old Skumanich prescription, they are all wrong, because they didn't include saturation, and only since 21 we started to incorporate saturation in our models. And the first thing we did actually was just take one of these saturated magnetic braking prescriptions. The details do not matter here. Just below you see this is a saturated prescription. Doesn't matter what all the variables are. Most of them are obvious. And then we just included boosting factor, because we need stronger magnetic braking for partially convective stars. And we included eta, which is a reduction of magnetic braking, the so-called disruption parameter. And with this new prescription for magnetic braking, actually, it works much better than it did before with the Skumanich prescription. It's actually really amazing. So the first thing we did was we looked at the main sequence binaries, and that's easy because we have a saturated prescription. So the predicted distributions should be flat, and the predicted distributions are flat. Wonderful, works, was an easy exercise. Then we looked at the distribution of the PCBs, where we had this decrease of systems, of short order period systems, at the fully convective boundary. And you see here, this is the same data I've shown in my old supernovae plot from 2010. This is the same data, just a different binding, so the values are not exactly the same. And you see this decrease, and you can fix it, and the lines are the predictions, and you can reproduce the observations if you have an eta which is like 50 or higher, and a K which is 50 or higher. So you need to have a significant boost, and you need to disrupt it at the fully convective boundary, then you can explain it. Still, it sounds weird to you, I think, just 2 parameters to fit these few points, not really convincing. But if you use the same model now, just that we applied to this type of systems, and you apply it to CVs, it works. Here you see the mass accretion rate as a function of orbital period. So the binaries start at longer periods. Here they start mass transfer, first very high, because you have efficient magnetic braking. They evolve towards shorter periods. Here magnetic braking becomes disrupted. The system detaches. We don't see them as CV anymore because there's no mass transfer. And then around 2 hours, they start mass transfer again. And the radii, the measured radii of the donor stars also fit very well. So here you have the measured values from eclipsing CVs as the stars, and here the evolutionary tracks calculated with MESA. You see that the radius is larger than it should be for systems that are partially convective, efficient magnetic braking. Then at the gap, when they become fully convective, the radius is allowed to decrease, which is also shown in the measurements, and then at relatively small radii, relatively close to the natural radius of the star, you see that we have a good agreement between the measurements when magnetic braking is weak. So and then actually we use the same prescription for other types of binaries. I don't want to go into the details, but we use the same prescription for double white dwarfs, and it works. We use the same prescriptions for AMCVN, and it works. So if you look here, it works for the main sequence binaries, it works for post-common envelope binaries, it works for cataclysmic variables. We have shown it works for white dwarf binaries. It's not yet published, but it works for this AMCVN binaries, which is a white dwarf accreting from a helium white dwarf, so two white dwarfs, but one is transferring mass to the other. We can explain the formation of these objects with this new magnetic braking that we were forced to use because Karim showed also in binaries magnetic braking saturates. And we are currently working on low mass X-ray binaries and ultra compact X-ray binaries, and it seems that also with the new prescription of magnetic braking, which is purely empirical and has these two parameters we just adjusted, but with the same parameter values, we can also explain these two types of systems. So it looks very convincing, like we might be getting closer to have one prescription for all types of binary stars. And now you say it's very different to what we say, what people in single stars have learned, but it's the same stars. It's not really clear what the difference is. So let me summarize. Single star and binary star people are separately converging towards empirical prescriptions that seem to work. We can do gyrochronology, we can explain features of pure distributions in closed binaries, and we also know that in both single and binary stars, magnetic braking saturates, so the dependence on period is changing. If you have really rapidly rotating stars, the braking doesn't increase further if you rotate faster, for really fast rotators. And then magnetic braking for partially convective stars seems to be stronger than in single stars. Why? We have no idea. And then we have this big disagreement what happens at the fully convective boundary. Single star studies show magnetic braking becomes stronger. In binary stars, it becomes weaker, and by a factor of 50. So this is really not clear what's happening there. And then in contrast to this, both argue for different dynamos in fully convective stars than in partially convective stars. Saturation occurs across the fully convective boundary, which could argue for the same dynamo. So now this contains a lot of problems, this slide, and I would like to show you my working hypothesis to perhaps as a bonus track, because my time is up actually, but I want to use one more minute, if you allow me, to show you what I think might be a possibility. So we have discovered one saturated magnetic braking prescription with a strong dependence on radius. It's actually the same one Matt proposed in 2015. And the strong dependence on radius actually allows us to fit the CV evolution, which you see here. This is, for example, the same plot with the radius measurements, just with different colors. And you see that the radius dependence actually is sufficient to explain this decrease. This break here doesn't need to be really dramatic. You can have just an eta of 3 and you reproduce the orbital period gap. So if we look at the orange line here, which is below the purple line here, it drops here exactly at 3 hours and it restarts at 2 hours and something. And you have a much weaker reduction than we had before. Still, you have a reduction by a factor of 2 in binaries, and you have an increase in single stars. What could be the solution for that? Now it's not that dramatic anymore. You don't have a factor of 50 and a factor of 2 in the other direction. You have two factors of 2 point something in different directions. And I think it could be related to the redistribution of angular momentum between the core, the radiative core, and the envelope. Because in single stars, if you have braking, the envelope rotates slower and slower, and the core rotates fast. So you inject angular momentum from the core to the envelope, which reduces braking. In binary stars, if you have braking, the envelope is accelerated due to the tidal forces. And because you have the accelerated envelope, the core rotates slower. So friction between the core and the envelope is reducing. It works as an additional braking in binary stars. And so we are playing around with this idea. So far, it doesn't work perfectly, but at least I think it's our working hypothesis to perhaps unify magnetic braking prescriptions in binaries and single stars. And I think the structure of the star, which we have ignored for decades, plays an important role. And we need to understand this properly. Before that, we won't really succeed. And my last slide is an announcement. We submitted a proposal to the Munich Institute for Astroparticle and Biophysics, which is an institute that offers funding for 4-week programs in Garching to invite experts from all around the world to solve one problem. And together with these friends here on this slide, we submitted a proposal to bring together the communities working on magnetic braking in single stars and in binary stars to basically sort out our differences and to learn from each other, because so far these two communities developed more or less separately. So we have to bring them together, and hopefully this program will be accepted, and then everybody who is interested can apply to participate. If everything goes well, it will happen in summer 2027. And yeah, if you're interested in magnetic braking and low mass stars and dynamo physics, you can apply then. Thank you very much for your attention, and I'm happy to take questions.
Thank you very much, Mathias, for the wonderful seminar. So any questions from the audience?
I have.
Yeah, can you come near the mic?
Hi, Matthias.
Hi.
How are you?
I'm good.
Do you recognize me?
Of course.
Okay. I do. Okay. Thank you very much. I really appreciate this talk.
Hope it was not too specific.
No, but it was great. Well, I'm gonna say I'm actually writing a paper about the pure distribution of CVs. And I've been having a lot of problems with the introduction, and you basically wrote the introduction for me. So
wonderful. What is the result? I'm interested.
Well, with Kepler that is there, and Lisa that is, we measure the period, the orbital period, or what we think is the orbital period, from tests like curves. So we took cataclysmic variables that were already classified as cataclysmic variables by spectroscopy mainly, and see if tests have data, look at the data, mainly Kepler did that, and determine the periods. Among them, the orbital periods. For some intermediate polars, we also have the spin period determined, and other periods that I have no idea what they are. And we got the period distribution. We have like 800 periods.
800 periods. Wonderful.
800 periods.
And homogeneously measured with tests.
Exactly.
Yeah, wonderful.
Only with tests. Yes. Actually, we also compare, we have like 350 that already have period determinations from the literature from, I don't know, many works. And
these insights, SDSS papers, for example, are very useful for them.
But we find, I think it's Inite, you use the data from Inite, Cambay, and others. Those are the ones that I remember. Actually, we compare the periods we got with the periods from the literature, and the distribution is quite similar. So actually, that was interesting. Anyways, and we're also comparing with rotations period from single white dwarfs. So that's why this talk was very useful for us. One thing that maybe you didn't mention that much here, but I wanted to ask you, when you consider that the binary, the cataclysmic binary, is synchronized, which period? Or for polars, we assume that because of the magnetic braking, the magnetic field, sorry, of the white dwarf. For intermediate polars, we do have the rotation of the white dwarf sometimes, but for others like novas or
No,
other
for
types,
so yeah.
when do you consider?
So synchronized is not fully synchronized in for CVs. It's always the donor star. So it was just an argument to make clear that the angular momentum has to be taken from the orbit, because the donor star has this magnetic wind and it's forced to rotate in synchronization. So the donor star is always synchronized. The white dwarf is a different story. The white dwarf can rotate much faster, especially if it's a non-magnetic CV. It is supposed to accrete all the angular momentum, then it's losing a fraction of this angular momentum in a nova eruption. We don't know really how much, but the most reasonable calculations I've seen that go back to a paper from Andy King, I think, they say that the white dwarf should spin up quite a bit. If it's just the outer regions of the white dwarf or the entire white dwarf, that's also not entirely clear.
Okay.
There are papers that say the white dwarf should start to rotate differentially, because the accreted angular momentum will not accelerate the entire white dwarf. I don't remember which one. I think Montgomery did this maybe some time ago. So the white dwarf is only synchronized in polars. In intermediate polars, it's synchronized with the inner edge of the accretion disk.
Okay, yes.
Which is different. And
yes.
in non-magnetic white dwarfs, I think it's really hard to measure. I think there are just a few examples of attempts to measure the rotation of the white dwarf in non-magnetic CVs. It's really hard because you have the accretion disk, and to really find the period of the white dwarf. I think there are some estimates from Paula Scoli a few decades ago. I'm not 100% sure if I trust them too much, but if I remember correctly, they found the white dwarfs to rotate relatively fast. So not at all synchronized.
So I cannot assume that SCP, the white dwarfs, is synchronized with the orbital period.
No, you should rather assume the white dwarfs in non-magnetic CVs is rotating faster.
Okay.
It's accreting all the angular momentum, and supposedly not all the angular momentum goes away during a nova eruption, because the nova eruption would need to be asymmetric to get rid of a lot of angular momentum, which is not usually assumed.
Okay. Okay, thank you.
No, thank you.
So any more questions?
I think Kepler has questions.
Yeah.
Okay, so we can move to the online.
Hi, Kepler.
Hi, Matthias. So in the 800 that Alejandra was talking, the 800 CVs, we have more than 100 eclipsing, we have more than 100 magnetics, and all the periods are very, very similar. The mean period is between 3.4 and 3.8 hours. So it's also very similar to the single white dwarf that we measured with Gabriela Oliveira that we published a year ago. So I'm surprised that all the stars that we have measured, anything from tests, have the same range of mean orbital or mean period. So either single stars that should be rotation, or CVs and novas and eclipsing, or in magnetic, everybody has periods around, mean periods around 3 and 4 hours. So
that's suspicious.
Exactly, but everything. But that's the reason that we did a very large number so that we could compare. So we have like 137 single white dwarfs. The mean is 3.4 hours. We have 100 novas, and the mean period is, I think, 3.6. We have non-magnetic CVs, and the mean period is 3.4. So I don't understand. What we think about transfer of angular momentum is not working.
Uh, I don't know. I mean, that would be one would need to look. Yeah, single white dwarfs. Then you measure it only of the magnetic ones, or you also measure
No,
periods
we have
non-magnetic ones.
both.
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 Yeah.
Oof, yeah, no, tough. I
Yeah,
don't
like
know. And if you look at the CVs, like it depends on the selection. So you used known, you looked at known CVs, right?
yeah, we looked at known CVs.
Known CVs,
And
just in the spectrum.
right.
And then there might be a bias in the CVs that have a spectrum that actually makes it likely to find systems around 3 hours. So that could make sense.
Okay.
Because they are between 3 and 5 hours, more or less. They are the brightest because the rate is relatively high. So maybe you find CVs further away than you do for the short periods. There should be actually more having periods below 2 hours. That's actually where people predict most CVs should have periods around 80 minutes.
Yeah, that's
But
not what
maybe
that's
these
not
are
what
too
we found.
faint. So maybe because of you would need the distance and see if the ones where you have longer periods are farther away. That could be an explanation why you find more of the longer period ones. So at the end, what you really want is a complete volume limited sample.
Yeah.
The distance, like up to 500 parsec, all CVs with 500 parsecs, then we know what is out there.
Okay.
And I would bet that if you do that, we have accumulation of systems at short periods, like 80 minutes.
Okay.
I would bet, I would put my money on that. I mean, maybe it's not true, but I would. I would
For the known, for the known CVs, not CVs, so the single white dwarfs, we did a volume correction, even though our sample is not, but we did not do a volume correction for the CVs because it's not complete yet. We still have another 500 CVs with test periods that we have not analyzed. So,
wow.
so there are many.
Yeah.
So at
That's
least,
pretty cool.
yeah, our sample is at least double of any previous sample, and like you said, it's very homogeneous. So, I think Alejandro will send you the draft as soon as it's ready.
Yeah, wonderful. Yeah, I'm interested.
Okay.
It's definitely a huge progress if you have more periods measured. That's
Yeah. Right. Thanks, Matthias.
I guess Horace, you have some message, some questions. Can you unmute and ask the question? Horacio?
Hello?
Horacio.
Hello?
Yeah. No, yeah,
Oh,
you're audible.
well, actually, our question of people that are not working in the area. Thank you very much, Matthias. I found an excellent seminar. You are a good lecturer, actually. But my question is magnetic string depending on stellar masses in single stars. And the other one is breaking seems to be fine-tuned to stellar temperature in single star. I mean, you have shown 4 groups of about 100 temperature interval each one of the group, and they are very different. It is
when I was talking about the fully convective stars,
single star, yes.
you
The
mean
one of the graphic before that one, before
this one?
that one, yes, right.
Yeah. This is the temperatures are relatively consistent. I think they are relatively well determined. But the key here is they use a gap in the Gaia HR diagram. There is a small gap. I think it's called the Yao gap, which separates fully convective from non-fully convective stars. because close to the fully convective boundary, you have this unstable helium-3 burning. This goes back to a paper from Van Saders et al. 2015, something like that. I don't remember exactly. And so this is related to the gap that you see in the Gaia HR diagram. And that is where they separated fully convective and non-fully convective. And then they have this temperature ranges. And yeah, there might be, of course, some mistakes where the temperature is not very well determined. But the main message of this figure is that no matter which figure you look, you see that the black ones, which are before you have this helium-3 burning instability, they have shorter periods than the red ones.
All right.
So that's the main message. And that's why they
Thank-
published it in Nature, I think, because yeah, it shows that fully convective stars break faster. And in binaries, we assume the opposite.
Okay,
Really
thank you.
cool.
Fine.
Yeah, thank you for the question.
Okay, then let's thank Matthias for the wonderful talk.
Thank you very much.
And I will see you guys next week on Wednesday. Bye-bye.
Bye.
Bye, Matías. Thank you.
Chao, Alejandra, nos
Chao.
vemos.
Te mando los gráficos después.
Thank you. Sí, por favor.